last class, we discussed that Maxwell's equation gave us field distribution. We considered the two Curl equations of Maxwell, and we saw that these two equations are coupled to each other. Although they are first order and they are linear in nature, but they are coupled to each other. Because of coupling, it is difficult to obtain the fields directly from these equations. Therefore, we started on a path of alternative for finding the solution of fields instead of using Maxwell's equation. So what we did is we took that divergence of B is equal to 0. This is what we know from Maxwell's equation. If divergence of B is equal to 0, we said that we can express B as a curl of some vector field. Therefore, we represented B as curl of A, and we called A to be magnetic vector field. In short, we called it vector potential. Similarly, for E, we started with curl of E is equal to minus dou T of B. From that, again we obtained E plus dou TA is equal to minus grad phi, and we said grad phi to be, we said phi to be scalar potential, or phi to be electric scalar potential. In short, we called it scalar potential. Then we saw one thing, vector A and the scalar phi are not uniquely defined. Why we said they are not uniquely defined? We said that B is equal to curl of A. For any vector to be uniquely defined, its curl must be defined and its divergence must be defined. Now curl of A is there, but divergence of A is not there, which means A is not uniquely defined. That also we saw from different points of view. Then we said something called gauge transformation, and for any scalar function, we said that E and B are invariant under gauge transformation. What is gauge transformation? That phi and A, if we add something to them, for example, to phi we added time derivative of a function, and to A we added gradient of a function. Function is f, which is scalar function. Then we call them phi dash and A dash. Now when we used phi dash and A dash, we expected to obtain a field which is E dash, but we saw that E dash is equal to E. So we established that under Gauss transformation, E and B are invariant. Invariant means they do not vary. Although we changed the potentials phi and A, but the net resultant in finding the fields E and B is unaffected. That is something that we found out. Then we used the curl of A or the B field. For B field, we used the curl of A and found out curl of E, right? So curl of E is equal to minus dou T B. Now if you take curl of B, that gives us dou T of E. So using that equation, using A for B is equal to curl of A, or B is equal to mu h, from which we found h is equal to 1 upon mu curl of A. We used that in h for finding out curl of h. When we found out curl of h, which is equal to dou d by dou t, we found out this equation. Del square A minus 1 by c square dou square t A, which is second derivative of A with respect to time. First one is nabla operation with respect to time, minus gradient of divergence of A plus 1 by c square dou t phi is equal to minus mu j. Now from this we obtained something called Gauss condition, Lorentz-Gauss condition, and that condition is divergence of A plus 1 by c square dou t phi is equal to 0. This was given by Lorentz. Now what is the rationale behind this? Assume that we are considering a charge-free or current-free space. Under that condition, the electric field or the magnetic field or any vector associated to the electric field or magnetic field behave like a wave. It can be a vector wave field, it can be a vector scalar, it can be a scalar wave field. Now if it behaves like a wave, it satisfies the wave equation. The wave equation is the first part. Del square A minus 1 upon c square, second derivative of time of A is equal to 0. If I put J is equal to 0, current is equal to 0, then that should be 0. Now to make this wave equation true in the absence of any source or in any source-free region, the wave equation must be satisfied. For that, Lorentz gave a Gauss condition, which is divergence of A plus 1 upon c square, time derivative of phi, that is to be 0. If that becomes 0, then this condition becomes satisfied. So with that, we proceeded further to find out if A and phi did not satisfy the constraint of the Lorentz-Gauss condition, then what is to be done? We said that if that is not satisfying, and then we will use the Gauss transformation so that this condition will be satisfied. To satisfy this condition, we can use Gauss transformation because we have already seen that under Gauss transformation, the fields are invariant. So what type of transformation? That also we said phi dash is equal to phi minus dou tf and A dash is equal to A plus grad of f. So that is the Gauss transformation that we can use. Using those Gauss transformation, we obtained divergence of A dash plus 1 upon c square, first derivative of phi dash with respect to time is equal to divergence of A plus 1 upon c square dou t of phi minus 1 upon c square dou t square f minus del square f. Now, f can be a solution of the inhomogeneous equation of del dot A plus 1 by c square dou t phi is equal to 1 by c square dou square tf minus del square f. Why? Because we have already said that if Lorentz condition is to be satisfied, then the left hand side is to be satisfied. A and phi are not satisfying the Lorentz condition, but we said that arranging or making a Gauss transformation, A dash and phi dash are satisfying the Lorentz transformation or Lorentz condition. So if A dash and phi dash are satisfying the Lorentz condition, then the left hand side will be 0. If left hand side is equal to 0, from the right hand side, we get divergence of A plus 1 by C square dou T phi is equal to 1 by C square dou square TF minus del square F. Now on this, the right hand side again is a wave equation. Left hand side is not a wave equation. The left hand side gives inhomogeneity to the wave equation. Therefore, we get an inhomogeneous wave equation which needs to be satisfied or which needs to be solved as we proceed further. Then we said that we knew 1 by epsilon into rho, rho is the charge density, is equal to divergence of electric field. For divergence of electric field, we can again write that 1 by C square, divergence of electric field, is equal to 1 by C square dou square T phi minus del square phi. This we have already seen. So for divergence of electric field, we replace this divergence of electric field. Now if we do that, then what we found is del square phi minus 1 by C square dou square 1 by epsilon rho and del square A minus 1 by C square dou square TA is equal to minus mu J. Now we got two equations. Both are vector, one is vector, one is scalar. When you have A, it is a vector equation. When you have phi, it is a scalar equation. But both are differential equations. Del square is a scalar quantity. Therefore, when we solve them, what we are going to get is either a scalar field or a vector field. But the vector field can be solved using a scalar wave equation. What does that mean? That means if we have three components of the vector A, each component of the vector A is satisfying this equation. Del square AX minus 1 by C square dou square TAX is equal to minus mu JX. Similarly for Y or for Z, or if we are considering spherical coordinate system, then same is valid for R, theta and phi. So for the vector part, we can get three distinct equations. Each equation is a wave equation and each one can be solved easily. Then also we saw that using these conditions, we can find out the continuity equation which establish that these conditions are equivalent to the Maxwell's equation. So instead of Maxwell's equation, we can use these conditions or we can use these potentials. Once we get these potentials, then we can go back to Maxwell's equation by finding out the fields using this potential. What is the condition of using this? H is equal to 1 upon mu curl of A, that gives me H. Once I found out A, then E is equal to minus grad phi minus dou T of A, that is equal to, instead of using grad phi, I can apply the Lorentz condition for grad phi and I can say dou T plus C square integration of gradient of divergence of A dt. Integrate that over T. So this is all this we are doing in time domain for the time being. So ultimately what we got? We got the solutions for those two wave equations, and the solutions are for the vector field ART is equal to 1 by 4 pi integration mu J R dash T minus R by C upon R dq R dash, which means dq R dash means it is over the whole volume. Similarly, a similar equation for phi. Phi depends on rho, A depends on J. So in case of phi, we get 1 by 4 pi epsilon. In case of A, we get mu by 4 pi epsilon, which are consistent to magnetic field and electric field. Now this we again try to look into a little bit in detail. For that we explained it in this manner, that suppose our source is at some point r dash. So throughout this lecture and throughout our course of study, when we complete this, till we complete this course, we will assume that the source is at a point r dash, and because of the source creates a disturbance, or source is the cause of radiation. Radiation is a disturbance. So because this cause, the effect of this cause is felt at a distant point r. So with respect to origin, the source is at r dash, and the observation point where we feel the effect of the source is at r. If that happens, then there is a finite time difference between the occurrence of the disturbance and observation at the observation point of the disturbance. Because of that, we define something called retarded potential. So this A and phi we call retarded potential. Retarded means retarded in time, which means it has occurred at a point of time which is much earlier than the time at which we are observing it. So this is what we discussed in the last class. Now let us take forward from this point onwards. So I'll start with time harmonic functions. Which are the functions that we call time harmonic? Or suppose we have a function w which is dependent on r and t, which means it depends on space as well as time. It has spatial variables and temporal variables. This function has two dependencies, therefore it is a time dependent function as well as it is a space dependent function. Now time dependency, when we say it is a time dependent function, the time dependency can be of any form. A particular form of time dependency is the function repeats itself over a given time period. So periodically the function repeats itself, which means it is harmonic in time. Harmonically it is repeating itself in time. Then we call it to be a time harmonic function. So if it is repeating itself in a particular interval of time, suppose we take that time to be capital T, then we know from elementary physics that T is equal to 1 upon F, which means T is associated with a frequency. So T is associated with one frequency only, it is not associated with many frequencies, it is associated with one frequency. Therefore, a time harmonic function will contain only one frequency. Now, if it contains only one frequency, then we can separate it into two components, which is the time component and the spatial component. Let us take the spatial component to be WR. The WR contains only the information about the space, and the temporal component to be e to the power minus j omega t. Why we will consider e to the power j omega t or plus j omega t? Why we will consider e to the power plus or minus j omega t? The reason is very simple. If we expand that, we get sin omega t plus, we get cos omega t plus j sin omega t. Or even if we don't expand that, we get e to the power j omega t. Now these are some functions using which we can expand any other temporal function in terms of a Fourier series. So if we have a non-time harmonic function that can be expanded using e to the power j omega t or sin omega t and cos omega t. So that gives us one reason for e to the power j omega t. The other reason is obvious, that if you take a sine function or a cosine function, something like this, sinusoidal functions, they are always harmonic in time. After a particular time interval, they repeat themselves. They are the most common time harmonic functions. So we take e to the power j omega t as our time dependence part. So if we do that, so let us define our vector potential as a time harmonic function. So if we do that, so vector potential ART will be divided into two parts, a temporal part and a spatial part, right? Now let us do that. How can we do that? Let us look at this. We defined ART, or we found out the solution of ART to be 1 upon 4 pi integration of mu j r dash t minus rc upon r dq r dash. Now the temporal part here lies in j, which is j is equal to r dash t minus r upon c. So t minus r upon c contains the information about time. So that is my temporal part. So I will do what? I will express j as j r dash e to the power minus j omega t minus r by c. So if I do that, I can write ART. ART I have separated into two parts, AR into e to the power j omega t. On the right hand side, I will get 1 by 4 pi mu j r dash e to the power j omega into t minus r upon c. Now that I can also write e to the power j omega t into e to the power j minus j omega r upon c. Let us take e to the power j omega t common. So in that case, and use the fact that k is equal to omega upon c. So once we do that, by taking that common, we will get e to the power j omega t outside, because the integration is only over space. It is not over time. So the time part we take outside. So it becomes e to the power minus j omega t upon 4 pi, then mu and j r dash e to the power minus j omega by c into r. Omega by c is equal to k. So for that we write e to the power minus j k r upon r dq r dash, which means the integration is over the complete volume. So now we have got AR e to the power j omega t is equal to e to the power j omega t upon 4 pi integration of mu j r dash e to the power minus j k r upon r d cube r dash. I hope you have understood up to this. Now if you have understood up to this, on left side and right side I have e to the power j omega t. So they will cancel out because they are not equal to 0. If something is 0, which appears on left side and right side, that we cannot cancel out, because 0 upon 0 is undefined. But e to the power j omega t is not equal to 0. Therefore, we can cancel that. Once we cancel that, for the vector potential, we get a term which is AR is equal to 1 by 4 pi integration mu j r dash e to the power minus j k r upon r dq r dash. So this is in the time harmonic form, the representation of AR. So once we find out a solution for AR, or once we find out what is my right hand side, then I can just multiply e to the power j omega t and find out what is the complete AR or ART. That I can find out by multiplying e to the power j omega t on both the sides. So this is the beauty of using time harmonic functions. It makes things very simpler. Now look at this equation which I have boxed. AR is equal to 1 by 4 pi integration mu j r dash e to the power minus j k r upon r dq r dash. Does it remind you something like the Fourier transforms? transform of J, you have read Fourier transform in terms of T. So if I replace R with T, then this will give me Fourier transform in time domain. In this case, what we are doing is, we are doing the same Fourier transform, not in time domain, but in spatial domain. Instead of time domain, time and frequency, we are now considering space and K. So K and R space. That is what we are considering instead of omega and T space. Now, let us look at what happens to the Lorentz condition if we use the time harmonic A and time harmonic phi. So, del dot A RT plus 1 upon c square dou T phi RT is equal to 0. What is this? This is the Lorentz condition. So, we start with Lorentz condition. Now, what we will do? For ART, we will write AR e to the power j omega t. For phi RT, we will write phi R e to the power j omega t. Now look at that. And dou t is operating on phi R e to the power j omega t, but phi R is independent upon time. Therefore, we can take that outside. So dou t will operate only on e to the power j omega t. So if we do that, then what we'll get? First term remains as it is. In the second term, we have taken phi RT outside. Dou t of e to the power j omega t is equal to j omega into e to the power j omega t. Therefore, we bring that j omega outside. J omega upon c square phi RT e to the power j omega t. Now that is equal to 0. Total is equal to 0. Now left hand side we can see e to the power j omega t is multiplied on each term, and that equates to 0, which means e to the power j omega t can be cancelled. Once we cancel that out, our Lorentz condition in the time harmonic form becomes divergence of A plus j omega upon c square phi is equal to 0, or we can say divergence of A is equal to minus j omega upon c square phi. That gives divergence of A is equal to minus j omega into mu 0 into epsilon 0, or you can say mu epsilon into phi, because 1 by c square is equal to epsilon into mu. As you know, speed of light c is equal to 1 upon root over of mu epsilon. So c square is equal to 1 upon mu epsilon. 1 upon c square will be mu into epsilon. So now our Lorentz condition looks much simpler without the time derivative. It looks much simpler, and what it gives us is, if we know A, somehow we find out A, we can find out phi. Just find out the time, just find out the divergence of A, which is only a differentiation. So once you find out the divergence of A, then divide that by minus j omega epsilon mu, that will give you phi. Otherwise, what would have happened? If we find out phi first, instead of A, if we find out phi first, then what we have to do is, we can find out the right hand side, but for A, we have to do one integration over the whole volume. You know, integration is a much tougher task or difficult task than differentiation. Therefore, this way it is always better to find out the vector potential instead of the scalar potential. Find out the vector potential. From the vector potential, find out the scalar potential. We can do the other way around, but that will create problem for us, because that will involve tedious integration. Now let us look at the Helmholtz equations. The Helmholtz equations in the time domain are del square A minus 1 upon C square dou square TA is equal to minus mu J. Now, once we come to the time harmonic case, A becomes AR e to the power j omega t and J becomes JR e to the power j omega t. Put those things in this equation. So that gives you del square AR e to the power j omega t 1 upon C square minus dou square T AR e to the power j omega t is equal to minus mu JR e to the power j omega t. Now, if you look at this equation, the leftmost part is dependent on space only, del square AR. Del square is not operating on T. On the rightmost part, there is no operation. We have a spatial variable and we have temporal variable. So spatial function and temporal function. The middle part, we have an operation in T. Dou square T is an operation on T. That will not operate on AR. So therefore, if we look at middle part, what we'll see, now find out this you should do yourself. That gives me, I am taking AR outside and dou square T e to the power j omega t. Now, you do the calculation. What will be there? If you calculate it, dou square T e to the power j omega t. Rest of the things we know, so we are not touching anything else except dou square T e to the power j omega t. Do the calculation. Mentally, you can do that. Dou square T e to the power j omega t is equal to minus omega square into e to the power minus j omega t. So now we have got 2 minus in the middle term. So that will become omega square upon c square AR. Now take e to the power j omega t common from both the terms on the left hand side. On the right hand side, you have got minus mu JR e to the power j omega t. Now we can cancel out e to the power j omega t. If we cancel out e to the power j omega t, what we will get is del square AR plus omega square upon c square AR is equal to minus mu JR. So our Helmholtz equation in the frequency domain or for a time harmonic condition, Helmholtz equation has been satisfied in this equation, and it becomes much simpler than considering the time domain condition. We have to solve this equation. The moment you look at this, now let me write omega square upon c as k square. If I write that, then this equation becomes del square AR plus k square AR is equal to minus mu JR. What is that? That is an inhomogeneous form of differential equation. Okay, so we get this I have kept in box because this is a very important. Whatever you will find boxed are important equations that we will use later. So del square AR plus k square AR is equal to minus mu JR is a differential equation on a vector A. Del square is scalar, k square is scalar, mu is scalar. What is vector? A and J are vector. Therefore, we can solve it for each component of A and each component of J. If we are considering spherical coordinate system, we can have it for AR, A theta, E phi, JR, J theta, J phi. So let us look at how we are going to solve this differential equation. So this is the differential equation which is at our hand. It is an inhomogeneous wave equation, and we are going to solve this inhomogeneous equation. What is the technique for that? First thing is obtain the Green's function or the G. G is called the Green's functions for this. Now remember one thing, if you have got an inhomogeneous wave equation, first thing is make it homogeneous. So right hand side, make the right hand side 0. Then for the wave equation, you will know what will be the form of the solution for A. Now when I make right hand side is equal to 0 in this equation, effectively what I am doing is I am making it source free. Now that means at the observation point, I am looking at A, and at the observation point there is no source. So at the observation point, the right hand side will be 0. So everywhere except at the source, the right hand side is equal to 0. So this is a homogeneous equation everywhere except at the source. At the source is there. So right hand side is not 0. That is something that I have to account for. How do you do that? At the source, assume that instead of j or minus mu j, I have got a delta function and solve it for the source at the source location. If I solve it for the source at the source location, and for A, if only there is a delta function, so that is satisfied by some other function g. That function I call g, Green's function. So instead of A, I will take g, and for minus mu j, I will take the delta function, and I will solve that. Once I find out the solution for that, then I will find out what is g. Then it is easy to find out A, because you know that from systems, signals and systems or communication, etc., if to us it is known what is the impulse response of a system, then the response of the system to any impressed function or to any impressed signal is the convolution of the signal with the impulse response. Now in this case, what I am suggesting is, for the right hand side we are taking delta. What is an impulse? It is a delta function. So for the right hand side we are taking a delta. Then if I solve that, I get g. For what I am getting g? For delta is an impulse. So I am getting g for an impulse. So once I get g for an impulse, if I replace that impulse with j, what will be the solution for A? A will be the convolution of the impulse response with j, which is convolution of j and g. So that is the technique. So first obtain the Green's function g, then convolve j with g. That gives you the solution for A. Now the question is how I am going to find the Green function. Finding the Green function is replace A with g on the left hand side. On the right hand side, I will replace that with a delta function. Our right hand side is replaced with a delta function. Then I will find the solution of the corresponding differential equation, which is del square gr plus k square gr is equal to minus del cube r. Why del cube? Because we are considering a three-dimensional case over whole volume. Why minus? What is the reason of taking negative? Because in our previous equation for A, on the right hand side we have got minus mu j. For mu j we are replacing an impulse function. So minus remains as it is. So you have got minus delta cube of r. Okay. So this is the inhomogeneous equation everywhere except at the origin. Why? Sorry, this is a homogeneous equation everywhere except at the origin. Why? We know delta R by definition is equal to 0 everywhere except at R is equal to 0. Therefore, except at origin or R is equal to 0, this equation is homogeneous everywhere. So first I will see for its solution everywhere, then I will find out what happens if I put the impulse. So for that, this del square G plus K square G is equal to 0 as a homogeneous equation. Now let us try to solve this equation or solve for the Green's function. So to start the solution, I will first write, we are considering this in the spherical coordinate system. Why we are considering it in the spherical coordinate system, or why I am using spherical coordinate system? In the first class, I think I gave you a hint and I told you about spherical coordinate system. What happens to del square in spherical coordinate system? What happens to delta in spherical coordinate system? That is what are the expressions for delta and delta square in spherical coordinate system. But I did not told you why I will use spherical coordinate system. That comes now. What we are doing here is, we are saying that at the origin, we have a point source. The source is a delta function. It has no expansion. As I expand R, this becomes 0. So it exists only at this origin, that is 0. R is equal to 0. It exists only there. It has only R dependence. Theta dependence is not there. If I look in the theta direction everywhere, in theta, if I vary theta from 0 to 90, at each point, I will see a point source at the origin. Similarly, as I vary phi on the phi axis or from 0 to 2 pi, at every point for phi, I'll see a point source at the origin. Only if I vary R, that is going to be varied, or that is going to have some effect. Therefore, I will consider only the R component. But before that, let us see what happens if I consider theta component and phi component, whether this logic is correct or not. So for the R component, we write 1 upon R square, dou R square dou R gr. Then for the theta component, plus 1 upon R square sin theta, dou theta sin theta, dou theta gr, plus 1 upon R square sin square theta, dou square phi gr. This will be this plus K square gr is equal to minus dou.
Hello, sir.
Yes. Hello.
Sir, is the authority को से R तक कमें नहीं वाला.
अच्छा हाँ, that I will tell you. Wait for a minute. I will tell you. Okay. So now what we are seeing is del square gr plus K square gr is equal to minus del cube r. Now del square gr we have expanded, and by expanding del square gr we are getting this equation 1 upon r square dou r square dou r gr plus 1 upon r square sin theta dou theta sin theta d theta gr plus 1 upon r square sin square theta dou square phi gr plus K square gr is equal to minus delta cube r. Now here we are independent upon theta and phi, which means dou theta is equal to 0, dou phi is equal to 0. Let me explain why dou theta is equal to 0, why dou theta is equal to 0 and dou phi is equal to 0. Once more, we are considering the source, which is delta r, or which is an impulse that is located at R. Right? R is a point at R, which is the origin. Origin is a point. So this source is a point at the origin. And it depends only on R, because we have the source is equal to delta R. delta is a function, so source is a function of r only. Now if I look from theta, why it is not a function of theta? If I look from theta, theta varies from, in a spherical coordinate system, theta varies from 0 to pi. At any point in the spherical coordinate system, take r fixed, make r fixed, then move from theta is equal to 0 to theta is equal to pi. On each point on your path from theta is equal to 0 to theta is equal to pi, you will see that there is a point charge or point source at the origin. There is no difference, no change in that. From everywhere you see a point source, which means what you are seeing or what you are observing from when we are varying theta is not changing. Your observation remains constant as you vary theta. Since observation remains constant, the observed value remains constant. It indicates that it is independent upon theta. Similarly, if you move for a fixed r, move on phi from 0 to 2 pi. Every point on that contour, on that path, you will find that what you are observing is constant, is a source point source. There is no change in that, which means the observation remains constant irrespective of phi. That means the observation is independent upon phi. Therefore, what we have taken at the center is independent, or the function for what we are considering as source is independent upon theta and independent upon phi. If it is independent upon theta, then dou theta is equal to 0. If it is independent upon phi, then dou phi is equal to 0. Now once I use this, then the second term and the third term on the left hand side will be 0. So therefore, this equation now will become 1 upon r square dou r square dou r gr plus k square gr is equal to dou cube r. Now we have to solve this equation. Now to solve this equation, let me make a substitution. In solution of a differential equation, essentially is integration of a differentiation. So dx dy by dx is equal to some function. You integrate both the sides, that gives you, integrate both sides with respect to x, that gives you y. That is the solution of the differential equation. Dy by dx is equal to fx. So in effect, you are integrating it. One of the method of integration you have studied is called the substitution method. So let me substitute something. For gr, let me substitute Lr is equal to Rgr. If I substitute Lr is equal to Rgr, then this equation will become dou square R Lr plus k square Lr is equal to 0, which means I have to solve for Lr easily now. It becomes dou square R Lr plus k square Lr is equal to 0. Solution is simple. Lr is equal to C1 e to the power minus jkr plus C2 e to the power jkr. C1 and C2 are two constants. Now look at what happens in this case. What happens in this case? Lr is equal to C1 e to the power minus jkr plus C2 e to the power jkr. What is e to the power minus jkr? It gives a outward propagation. Something is which is moving outward from the location 0. So C is equal to 0, sorry, R is equal to 0. Then as you keep on increasing R, this function will become effective. In the other case, it is an inward propagation. E to the power jkr is a inward moving wave or inward moving function, whereas e to the power minus jkr is an outward moving function. What we require, we have a source at the origin. So nothing will move towards the origin, at the origin, right? Because the source is at the origin, it will propagate away from the origin. The resultant will propagate away from the origin, which means this second part, e to the power jkr, has no significance. It is not going to contribute. How do we will deal with this? We will do one thing, simple thing is make C2 is equal to 0. C2 is a constant. So make C2 is equal to 0. That takes care of the second term. There will be no second term. So with this physical reasoning, we get that C2 is equal to 0. Therefore, LR is equal to C1 e to the power minus jkr. Now what is our function? GR is equal to 1 upon LR. So this will be 1 upon R. Sorry, GR is equal to 1 upon R into LR. Therefore, GR will be 1 upon R into C1 e to the power minus jkr. Now, the task is to find out what is C1. We have found out C2 to be 0. Now, if we find out C1, what is the value of C1, then our job is done. We will be happy. GR will be found. Once GR is found out, we can find out A. So our task is to find out what is C1. Now for that, remember one thing, we are using an impulse function, spatial impulse function, but it is impulse. In nature, it is impulse, which means this function will exist only when r is equal to 0. That is why we'll consider the limit r goes to 0. So let us find out what happens when limit r goes to 0 and we use the differential equation. So for the differential equation, what we have? 1 by r dash square dr over r dash 2 r dash square dr 1 upon r c1 e to the power minus jkr. This was the first part. Other parts of the differential equations were 0. Theta and phi were 0. Only r dependence were there. Now remember, these all should be r dash. Some r are there. Those are all should be r dash. Or for the time being, take r dash is r. For the time being, let us take r dash is equal to r, and finally we will consider r is equal to r dash. Why? The reason is r dash is the location of the source, r is the location of the observation point. That is the reason. Okay, now in this case, this is my differential equation. To find out the solution, what I have to do? I have to integrate of both the sides of the differential. I have to integrate both sides of the differential equation. This is over the volume. Therefore, I have to integrate it over the complete volume. I am considering the spherical coordinate system. So if I have to integrate it, then I have to integrate it over which variable? R square sine theta dr d theta d phi. That is the elementary volume. So over that elementary volume, I have to integrate. For r, it is from 0 to r, limit is from 0 to r. For theta, limit is from 0 to pi. For phi, limit is from 0 to 2 pi. So I have to take a triple integration on the left hand side as well as on the right hand side. So for the right hand side, it is dq bar only, or sorry, delta q bar, and dr dash, dv dash, that is not dr dash, dv dash, or dr cube dash, or dv dash. Now right hand side, you know what will be that. Delta function integrated over the whole space gives you 1. Integration of delta r dr minus infinity to infinity is equal to 1. Therefore, I know what will be my right hand side. Now what will be my left hand side. That is what is important to me. So let me find out what will be my left hand side. So for the left hand side, first let me integrate over d phi. D phi, you see that function contains no function in phi. So integration over d phi is simple. Integration 0 to 2 pi d phi. That gives me 2 pi. Then for the theta, only I have got sine theta d theta. So integration from 0 to pi sine theta d theta. Sine theta d theta integration, you know, minus cos theta. So minus cos theta, limit is from 0 to pi, right? Minus cos theta, cos pi is minus 1. So minus cos theta or minus cos pi is 1. Then minus of minus cos 0, minus cos 0 is 1. So minus of minus 1. So that will give integration over theta will give me 2. So 2 into 2 pi will give me 4 pi. So that 4 pi I have taken outside. So what is left is only r part, right? Only the part with r. If I integrate that, that is going to give me jkr plus 1 e to the power minus jkr. That is very easy. You can do it yourself in the class or try it in the evening. See that the integration over r gives you minus c1 into jkr plus 1 e to the power minus jkr. Then the second term will be minus 4 pi k square. 4 pi is constant in both the cases. Minus 4 pi k square. Integration 0 to r e to the power minus jkr r dr. Right hand side is equal to 0. Now the interesting part comes. R goes to 0. If r goes to 0, the second term is e to the power minus jkr. R goes to 0, that is 1. Then r dr, r goes to 0, that is 0. So the second term becomes 0. Minus 4 pi k square into 0. So contribution to due to that, as we go to 0, as r goes to 0, contribution due to that is equal to 0. Now what is left is the left hand side, first column. 4 pi into minus c1 jkr, as r goes to 0, that is 0. Then e to the power minus jkr, r goes to 0, e to the power minus jkr is equal to 1. Therefore, what I have got is 4 pi into minus c1 on the left hand side as r goes to 0. So that gives me minus 4 pi c1, left hand side is equal to 1, from which we can see that c1 is equal to 1 upon 4 pi r, right? So we have found out the Green's function. So the general form of the solution for Green's function is gr is equal to exponential of minus jkr upon 4 pi r. Now let us examine this little bit. Now when we have put the source at the origin. Now if I put r is equal to non-zero, if r is equal to 0, this becomes a delta function at the origin. If r is not equal to 0, as I proceed with r, for any value of r, what I will get is at any distance of r over a radius of r, the numerator, which is the exponential minus jkr, if I take a constant r, that remains constant. Now you know exponential jkr gives you the phase. So over that value, over any constant r, so for a fixed r, the phase remains fixed. But as I keep on changing r, the amplitude keeps on decreasing, right? Because there is a 1 by r term. So as I move away, amplitude decreases with distance, but over a constant R, the phase remains constant. What does that mean? That means we are getting a spherical surface on which the phase is constant, and as we expand the radius of the sphere, the amplitude goes down, but the phase remains constant over a spherical surface. You know that when phase is constant on a wavefront, we call that wavefront to be the nature of the wave. So in this case, the nature will be spherical because the constant phase is over the surface, over a surface which is a sphere, right? If I take a plane, it is not constant. So if we have a point source, then we'll get spherical waves. This is one of the important conclusions when we start with green functions or when we look at antenna. If I take a point source at the origin, I will not get a plane wave, I will get a spherical wave. Right. So this is equivalent to the response of the potential to an impulse excitation that we have seen. Therefore, the solution to the potential A will be AR is equal to mu JR dash GR minus R dash dq bar integration, which is the convolution. So we have found out what will be the solution for the potential if we are in the time, we are considering time harmonic case. So time harmonic case makes our life somewhat easier. Now let us look at, once we know the potential, we can find out the field. You remember divergence of A is equal to minus j omega epsilon mu phi. This comes from Lorentz condition, or phi is equal to minus divergence of A upon j omega mu epsilon. So remember this always. Right. Now let me first start with the H field. H is equal to 1 upon mu curl of A. Then E is equal to minus grad phi minus dou TA, and for dou TA we have written this dou T minus dou TA plus, if I replace grad phi, I get C square integration gradient of divergence of A dt. This is a cumbersome equation. I don't like it. Neither you like it. Nobody likes such cumbersome equation. Now once we go to time harmonic field, then E becomes, this equation simplifies. E becomes minus grad, in place of phi, write minus grad, the grad A by j omega epsilon mu. So put that minus grad of minus grad A by j omega epsilon mu. Then minus dou T is equivalent to j omega if I am considering a time harmonic case. So minus j omega A. So instead of the previous equation, what I have got now is gradient of divergence of A upon j omega epsilon mu minus j omega A. So compare it with the upper one, the portion highlighted in yellow. Compare that with the portion highlighted in green. It is much easier. The greener one is much easier. It's a greener patch. Right. Therefore, I can find E as E is equal to 1 upon j omega epsilon mu into gradient of divergence of A plus k square A. Right. So that gives me E. Now let me give you a homework that proves that E is equal to 1 upon j omega epsilon mu curl of A in the source free region. Not a homework. Let us, okay. So take it as a homework and prove this. E is equal to 1 upon j omega mu epsilon curl of A in a source-free region. Hint is, in the source-free region, you have got J and rho equal to 0. There is no rho, there is no J. So use that and prove this. Right. So let us go back to what you have studied in your school days or early college days. Let us look at the dielectric polarization. So revisit the dielectric polarization. You know that in the presence of external or free density, charge densities or current density in a material medium, if you have a material medium like a dielectric, not free space, I consider a material medium like a dielectric, and if I put external or free charge densities into that, or external current into that material medium, then what will happen? This will induce dielectric polarization in the material. This induces dielectric polarization. The polarization is given as epsilon 0 xi into E, where xi is called the susceptibility. So what is this susceptibility? That also you have studied, that this is a measure of electric polarization property of the material. Right? So this is the average electric dipole moment per unit volume. How to find this xi? Take the average electric dipole moment per unit volume. That gives you xi, and it is a measure of electric polarization property of the material. This xi manifests in the flux density. That is, the flux density, electric flux density, can be expressed in terms of xi using epsilon, which is the dielectric constant. So epsilon is equal to epsilon 0 into 1 plus xi. Use that in the flux density equation. D is equal to epsilon E. Epsilon is equal to epsilon 0 into 1 plus xi. So that into E, that is equal to epsilon 0 E plus epsilon 0 xi E. That is equal to, first part remains as it is, epsilon 0 E, plus the second part we have seen, P is equal to epsilon 0 xi E. So epsilon 0 xi E, I can write P. P is the dielectric polarization. This thing is encompassed in the Maxwell's equation, or Maxwell's equation includes these through the curl equation for B. Curl of B is equal to mu 0 epsilon 0 dou E by dou T. Actually, this is curl of B is equal to mu 0 dou D by dou T. Right? For dou D by dou T, if I replace the dou D from the above equation, I will get this much. So mu 0 epsilon 0 dou E by dou T plus mu 0 J, that is the conduction current, plus dou P by dou T. Okay. So then divergence of E, that is equal to 1 upon epsilon 0 into rho minus grad of P. This also you know from Maxwell's equation. How? Divergence of E is equal to 1 upon epsilon 0 into rho. Now we have seen rho, we can put rho as rho minus grad P, depend from the flux density. D is equal to epsilon 0 E plus P. From that we can put rho is equal to rho minus grad P. It's a divergence P. So current and charge densities due to the material polarizations are now J polarized, means polarized current is equal to dou P by dou T, and polarized charge is equal to minus divergence of P. So we get or we complete our revision of dielectric polarization. Remember one thing, the polarization here is for the polarization of material molecules. The molecules in the material, how they are polarized in the presence of an external field. This is completely different from the polarization of fields, which is in free space, which is in charge-free or source-free space. In source-free space, polarization means the orientation of electric field. When you have charge or you have a source, then polarization means dielectric polarization or orientation of the molecule or response of the molecules to of a material to an external electric or magnetic field. So with this, we will take some rest